Hello, Dr. Birch, and anyone else who happens to happen upon this video. I'm doing my test corrections for exam number 3, specifically questions number 3 and 4 on the white paper. I got number 3 wrong because I was confusing the power series with geoseries, and geoseries has a common ratio, and as long as the magnitude of that is less than 1, then the series will converge. Okay, so for problem number 4, I'm going to go through each one of my examples and explain why they are wrong in particular. So for the first one, I have the magnitude of x minus a is less than 1. And so for this one, I had associated it with the geoseries, which as long as the magnitude of x is less than 1, it will converge. And I was using a as a variable instead of c, because I took this answer from the form of the power series, which is a sub n times x minus c to the n. For the remainder of my original answer, I had put the series that was represented by cosine of x, and I knew that this one had a radius of convergence that was infinite, and then for the last one, I was simply grasping at straws, and so I just wrote another series that was explained around the same time as when we were talking about radius of convergence in class. Okay, so I'm actually going to be doing problem number 4 before problem number 3. There are 3 general scenarios for different radii of convergences for power series. I'm going to list each possibility and give an example of a power series for each scenario. Okay, so for our first example, we're going to have a radius of convergence that is between 0 and infinity. And with this example here, we're going to do the ratio test real quick. So it's going to be a sub n plus 1 over a sub n, or in this case, the reciprocal of that. The x to the power of n cancels out, and so I'm just going to rewrite this real quick with the x on the outside. We're going to have that times the limit of n approaching infinity, n over n plus 1. This is going to be equal to 1, so I'm just going to rewrite this as the magnitude of x. And as long as this is less than 1, it will converge. And so there we have our radius of convergence, which is between -1 and 1. An important note to make here is that we do have to test the bounds to see if we can include those in the interval, and so we're going to test those individually by plugging in the bounds for x. So here we have -1 to the n over n, and then we have 1 to the n over here. And so this one just simplifies out to 1 over n, and because this is the harmonic series, we know that it diverges. And over here we have a similar story. This would become 1 over n whenever you're doing absolute value of that. And so this would also become the harmonic series, which also diverges. And so our bounds would be -1 to 1, non-inclusive. So for the second general scenario, we're going to have a radius of convergence that is infinite. And so with this one in particular, I chose the series that is representative of e to the x. And we're going to take the ratio test of this one real quickly. So that's the limit as n approaches infinity. We're going to do the absolute value of a sub n plus 1 over a sub n. In this case is going to be the reciprocal of that here. And then we're going to cross cancel these here, and then we're going to cross cancel these. And so we're left with the magnitude of x times the limit as n approaches infinity for the absolute value of 1 over n plus 1. Okay, and this is just going to be equal to the magnitude of x times 0, but because that's going to be 0 for any value x, we know that the interval of convergence will be less than 1 for any given x, and so therefore the radius of convergence is infinite. So the last general scenario that we have is whenever the radius of convergence is 0, and that's going to be whenever it's a single point. As you can guess, that's going to be at the center, and I'm going to prove that with the ratio test here real quick. So we're going to do the limit as n approaches infinity for the absolute value of a sub n plus 1 over a sub n. Okay, these are going to cancel here. We're left with a absolute value of x. Okay, and these are going to cancel here. So we're left with the limit as n approaches infinity for the magnitude of n plus 1 over 1, which is just infinity. So you're going to get magnitude of x times infinity. And so for any value other than 0, this is going to be greater than 1, and so it would be divergent via the ratio test. And because whenever x equals 0, it would be less than 1, and so that's how it would converge for that point on the center, which is 0. Okay, so it is not possible for a power series to diverge for all values x because any given power series will always converge at its center. I'm going to show you that here. Whenever you look at the center, that's when x equals c. We're going to have the series here as follows: a sub n, c minus c to the n. This is going to be equal to 0, so I'm just going to write 0 here. Now, if we look at the terms for this series here, we will have a sub 0 times 0 to the 0th plus a sub 1 times 0 to the first plus a sub 2 to the power of 2, etc. And if we look at all the terms here, we will have 0, 0, 0, etc. except for this first one, because 0 to the 0th power is defined as 1, and so we have a to the 0, a sub 0 times 1 plus a bunch of zeros, which makes this series actually equivalent to a sub 0. So we can see that because the series converges to a sub 0, whatever it may be, we know that any power series at its center will be convergent. And so because any power series will be convergent at its center, we know that it can't diverge for all of x.